All right, everybody, welcome back to Hall 6. Now, what I learned from the last talk is that, of course, telemetry is great, observability is a must-have, but you also need storage to persist your data. So this talk is going to be about storage. As for our speaker, he really had a tough race to come to Vienna since he received his visa on Monday, went straight to the plane, flew here to Vienna from Nigeria. So please give a warm hand to Israel Geoffrey, who is a vivid open source contributor. He's a storage expert, and he's currently working as a software engineer at SimplyBlock. The stage is yours.
Thank you. All right. So today we'll be looking at streamlining storage lifecycle automation in Kubernetes, SPDK-CSI as our use case. So jumping there, as Daniel introduced, I'm Israel Geoffrey. I'm currently working with SimplyBlock as a software engineer. So today, our agenda for today, first we'll open up with an introduction to Kubernetes storage management. Why do we really need storage in Kubernetes? And then we'll move down to introduction to, just a little introduction to SPDK, what SPDK really is. And then down there, we'll move over to container storage interface, CSI. We'll talk about CSI, workflows of CSI, how to go about CSI. Creating and managing storage classes, dynamic volume provisioning, implementing snapshot and cloning, and then we'll go into conclusion. So first, I believe everybody here knows what Kubernetes is. For those who don't know, Kubernetes is a container orchestration platform for automating deployment, scaling, and managing containerized application. So one of the key features of Kubernetes, I believe it has so many other key features. One of the key features is automatic scaling, self-healing, and rolling of updates. So it is easy to roll new updates with Kubernetes. So the other question is, why efficient storage management? So why efficient storage management? We need dynamic and scalable storage. We need storage that can be able to grow with time. So we need storage that we can add as storage continues to grow. We should be able to continue adding storage and have an unlimited storage capacity. So, and also as technology keeps growing, we have so many complex systems, some distributed systems. So it is paramount to have good storage solution to be able to handle these distributed applications. And also distributed application, we're also looking at performance. Performance is a good thing in storage, especially in the areas of AI, where we have a lot of performance is key paramount for LLM models. So, and also look at data availability. Data availability, we should also be able to have storage not only run on a particular vendor, but that storage should run cloud agnostic. It should run across cloud providers and also on premises. So we should be able to move storage around, or data around rather, move it around from cloud storage to also on premises based on company's choices or enterprise choices. So just a brief introduction to SPDK, nothing deep, but there is a lot going on in SPDK. Just a minor introduction, just to give us an overview of what SPDK is. So SPDK is an open source framework developed by Intel for designing high performance storage application. So SPDK gives us the user access to storage hardware like the NVMe SSDs. So with the user having access to NVMe SSDs, it provides the availability for low latency and high throughput by bypassing the Linux kernel. So SPDK supports technologies like the NVMe over Fabrics. So with NVMe over Fabrics, we can have remote access to NVMe device, and also with the remote access to NVMe device, we can achieve what we call aggregated storage solution. So behind the scene, SPDK runs behind the DBDK, the Data Plane Development Kit. So the Data Plane Development Kit is what gives the SPDK the efficiency for managing high-speed packet processing. So with all this technology going on, it makes SPDK the ideal for modern storage infrastructure where performance is critical. So if you're a company where storage performance is critical for you, I would suggest you use SPDK, or you could refer to SimplyBlock, the organization I work with, to work with our storage and also embed with SPDK-CSI to achieve high performance using NVMe and NVMe over Fabrics. So that is just a brief introduction to SPDK. So what exactly is CSI? So from my understanding, CSI is an industry specification designed for running storage solution on container orchestration platform like Kubernetes. So CSI gives us the availability, CSI gives us the feature to decouple storage from Kubernetes. So early days in Kubernetes, storage vendors had to write their own plugins within Kubernetes, but with the introduction of CSI, we have a decoupled system where the CSI lives outside of Kubernetes, and it makes it easy for both Kubernetes development and also CSI. So storage vendors focuses on just development of the CSI drivers and their key features to achieving the CSI driver. So with this, it amounts in rapid development, shipment of new versions of CSI drivers. So next, we have to talk about the three components of CSI driver. So first, we have the controller service. So the controller service manages the storage resources. Any of the storage resources that doesn't need to deal with resources that run directly on the node, like creation of dynamic volume, snapshot, volume expansion, volume health monitoring. So these are done in the controller service. So the controller service has key endpoints, or rather key functions. We have the create volume, the publish volume, the unpublished volume, and the delete volume. In my next slide, I will talk deeply about what this does and the workflow, how all these are connected together. So also the node service. The node service mainly is responsible for features or functionality that needs to run on the node itself, where the pod is mounted. So the node service works when the pod tries to mount on the PVCs. So we have key features like formatting of the file system, in case we're using a file system type, mounting of the volume, and exposing of the volume of the path to the kubelet. So for the identity service mainly just communicates to the Kubernetes API, gives you the knowledge about the CSI driver, the capabilities of the CSI driver, the function of the CSI driver, and the name of the CSI driver. You can see it as a way of making Kubernetes, the Kubernetes API aware of the existence of the CSI driver. So that is what the identity service does. So next, I want to walk through the workflow from the moment you create PV, what happens up to the moment of where the pod mounts to the PV. So first, when you create a PVC, that is in a general and dynamic volume provisioning sense. So the Kubernetes plane API communicates to the CSI driver and create volume endpoint. It communicates to the create volume endpoint, telling that I want to create a volume. So the create volume endpoint is what has all the logic for creating this volume. It creates this volume and then gives this volume a particular capacity based on the specification defined in the PVCs. The capacity, the access mode, the create volume is responsible for creating of the persistent volume. And it communicates to the storage backend, that is the storage vendor own storage solution, using an RPC communication, an RPC. So when this volume is created, the next thing is during the pod mounting, for a pod to mount these PVCs. So what the controller service does is controller service looks at the pod where the node where the pod is running, and then it attaches this PVC to that particular node. So when this PVC is attached to this particular node, then the next service takes place. The next service takes place, which is the node service. So basically, the node service, the staging stage. What it does is can have many volume operation, mainly for us. That is where we do the file system formatting. So we format our file system based on file system type, if it's EST4 or SFS. So there you format the file system in the stage volume stage. So you can see the stage volume stage as a stage where you prepare the volume before the mounting. You do all the necessary preparation before mounting the volume. So after that, the volume is prepared and ready for mounting. Then the node publisher endpoint is called. The node publisher endpoint is responsible for mounting this volume to the pod and making this volume available for the pod to use based on a particular path on the kubelet. So when this is done, in the reverse sense, when you delete a PVC, what does is, on the reverse first, it unmounts this volume by calling the node unpublisher volume. The Kubernetes called the node unpublisher volume to unmount the volume. So when this volume is unmounted, then the unstaging step takes place. Maybe you want to fix some run some background tests or run some background cleanup of your mount prepared file system. So after that is done, the next step is called, the Kubernetes API calls the controller unpublished volume. The controller unpublished volume detach this PV from the node, from the worker node, making this PV available in case any other pod tries to mount this PV. So after that is done, the delete volume endpoint is called. The delete volume endpoint is what does the final cleanup by deleting the PV and deleting the persistent volume, or it could retain the persistent volume based on the reclaim policy you set. So that is the workflow of Kubernetes API with CSI, how Kubernetes calls volume and how the volume gets mounted to the pod, and how the volume gets unmounted and deleted. So deploying SPDK on Kubernetes. So for us, ideally we use Helm chart to deploy our SPDK-CSI on Kubernetes. So there we set a lot of parameters like the simply block UUID, the IP, the secret, to communicate to our simply block management plane. So to make this storage available to the CSI driver. So you could set, we use pool to group our logical volumes, so you can set the pool name. You can set the pool name testing one. You can also have a lot of parameters. We have a lot of parameters. Well, these are the key or basic parameters to create to attach the CSI driver or to configure the CSI driver with our storage vendor, simply block. So creating and managing storage class. So for the creation of management of storage class, first we have the API version, the kind, which is kind storage class. So the key point here is the provisioner. If you look, I used an arrow to point this. So the provisioner should match the name of the CSI driver. And the CSI driver, I forgot to mention, it is packed as part of the Helm chart, and also with the controller service, the node service, the identity service. These are all packed as part of the Helm template and then deployed. So due to time, I couldn't demonstrate this. It would take a lot of time to go through all these steps. But the key point is the CSI driver. The CSI driver name should match the storage provisioner name should match the CSI driver name. Like I mentioned like I showed in the arrow, the provisioner name should match. And also in the parameter session where you configure your parameters based on your volume specification or the parameters you need for your volume. So we have the file system type, which is EST4, the pool name, like I mentioned before, the pool name you want to attach the volume. So whenever the volume is being created, the logical volumes, which pool they belong to inside of the simply block storage plane. So we have other parameters, the compression, the encryption. And then for the reclaim policy. So the reclaim policy is ideally talking of what happens when the particular PVC, when a PVC is created, it dynamically creates a PV. So when this PVC is deleted, what happens to the PV? So by default, it has the delete. So when a PVC is deleted, it dynamically deletes the associated PV. So you can also set other values like the retain. So for the retain, when a PV is deleted, the associated PV to that PVC remains. So you could do further configuration for another pod to assume this PV. So for the volume binding mode, so the volume binding mode is kind of talking about when doing the dynamic volume provisioning of the PV, when the PVC dynamically provision the PV, right? So what happens? It's immediately bound to the PVC. The PV bounds to the PV. So we can also set other parameters like wait for first consumer. So it will not bound to the PV. The PVC and the PV won't bound until the next consumer is available, which is a pod. When the pod tries to mount these PVs, that is PVC. That is when the PV gets bound. So for the volume expansion, setting to true. So for this feature to work, you need the controller sidecar, which is the external resizer, the volume resizer. You need this feature so you can be able to, when a particular PVC or when a particular PV is created with a particular volume size or capacity, so you can still increase the capacity based on demand, you can increase the capacity, and then it will dynamically increase the capacity in the storage plane. So that is it for managing storage classes, Kubernetes. So here, the steps for the dynamic volume provisioning. The step for the dynamic volume provisioning, so like mentioned, from the already existing storage class, the persistent volume claim must reference the storage class which it wants to attach itself to. So the storage class name and the name of the storage class should match, like I highlighted here in my chart. So also for the access mode I used here was read-write once. That means any pod that attached to this persistent volume can have the capacity or capabilities to read and also write to the file system, to the volume. So for the request and resource requester, so when the dynamic volume provisioning, the PVC is trying to create the PV, we're trying to create a PV with a particular capacity of 2 giga. So it creates a PV with this particular capacity. So this persistent volume claim dynamically creates the PV based on with the particular capacity of 2 giga, based on the specification here. So next, I want to move into demo to show how to create a dynamic volume provisioning and also show how to deploy this storage class in our Kubernetes cluster. So permit me a second to switch over to my terminal. So first, so this is our storage class, like I explained earlier in the previous slide. So we'll go ahead and provision the storage class on a particular namespace. So to do that, go ahead and kubectl apply -f. So provisioning the storage class on the SPDK-CSI namespace. So now we'll create the storage class. The storage class is already created in our cluster. So the next step is the PVC, to create the PVC that will reference the storage class. So here is our PVC, like I showed earlier in the previous slide. So we'll go ahead and provision this PVC. Also in the SPDK-CSI namespace, first to have them all in the same namespace. So like you may see here, so we already have the PVC is created. So based on our storage class and specification, we have the immediate to bound immediately. So that is why the PVC is bounded to the PV immediately. So the capacity that was specified in the PVC, the access mode, and also it referenced the storage class which the PVC belongs to. So after this, the next step I want to go into, go back to my slide. Sorry. Okay, that is all for demo 1. So for demo 2, for the next step, the snapshot and cloning. So for snapshot and cloning, it's an entirely different thing. That is, ideally CSI drivers by default doesn't come with this. So one of the basic features or sidecar for a CSI driver is the external provisioner and the external attacher, which are just the basic for creating dynamic volume and attaching that volume to a node. So to have features like snapshot, we also need to enrich our controller, our CSI controller, with more capabilities. Like we create a new function, that is the create snapshot, the leave snapshot, and the delete snapshot. But before this can be done, we first need to install some CRDs and controllers, because Kubernetes core API by default doesn't have the snapshot and also the snapshot API. So by installing the snapshot controller and its CRDs, it enriches Kubernetes with these functionalities, so Kubernetes can be able to dynamically, can be able to create this, can be able to create and manage snapshot, can be able to manage snapshot. So when I was supposed to show this on here, but due to time, we also was able to install this as part of our Helm chart. So the CRDs, the snapshot controller was installed as part of the Helm chart. So for industries or enterprise that want to embark on CSI driver, it is convenient and much best practices to install this as part of your Helm template. So while the users focuses on creating the resources like the PVCs, the snapshot, the volume snapshot, and maybe the volume snapshot classes in the user side. So this does the same way the dynamic volume provisioning is done. So when we try to create a snapshot, the Kubernetes API calls the create snapshot functionalities to create this snapshot on the CSI side. So the CSI creates this snapshot, and it creates what we call a volume snapshot content. A volume snapshot content is what contains, is where the actual snapshot content exists. So when the actual snapshot content exists, so in the next slide, I'm going to show how this is related. Mostly they are the same with PVC. So we can see the volume snapshot class as a storage class, where the parameters for the snapshot is set. And also we can see the volume snapshot as as a PVC responsible for dynamically creating the snapshot content. It creates the snapshot content. So, so this is basically the implementing of snapshot. To implement snapshot, first you need to install the volume snapshot class. The volume snapshot class, as you can see, it looks somehow similar to the storage class. It references the CSI driver also, which is the csi.spdk.io. It also has the deletion policy. The deletion policy is similar to the storage class, which is when it's stating that when the volume snapshot is deleted, what happens to the snapshot content? What happens to the snapshot content? So for here, we have delete. You can also have another parameter of retain. That is when the volume snapshot is deleted, we should retain the snapshot content. So to have a snapshot, after creation of the snapshot class, the next thing we need is the volume snapshot. The volume snapshot references both the volume snapshot class name and also the persistent volume claim to create this snapshot from. Let's look from the arrow over here. We reference the name, the volume snapshot class name should reference the volume snapshot class name and also the persistent volume claim name. So with this, it dynamically creates the volume snapshot content. And then from here, we'll talk about restore, which is the next thing I want to talk about. The volume snapshot. So to achieve restoration, let's say in the case of disaster or in the case you lose your data, so it's paramount to have backup. So to achieve this backup, first, when the volume snapshot is created, which creates the volume snapshot content, for it to arrive in the state where the PVC was during the snapshot, or to restore your data back. So you need to introduce what we call the data source in the PVC. So the data source in the PVC is telling the persistent volume claim that we don't want to create a new PV, but rather we want to create a PV from a source. And that source has the API groups, the kind. So the kind, we're telling the persistent volume claim that is the source is from a volume snapshot, and then we give the API group. Since snapshot by default is not part of Kubernetes core API, so we need to reference the API group. So the persistent volume claim is able to get the snapshot. So also need to reference the access mode and then resources, just like the other persistent volume claim which I showed. You also need to reference other parameters like the access mode and the request, which is storage capacity of 2 GB. So it will create this snapshot. It will create a new PV based on this from the snapshot of capacity 2 GB. So here, to go ahead and show the second demo. So for the second demo, first we need to create the volume snapshot class. Okay. So this is the snapshot class, or rather, let me clean this. So this is the snapshot class, the volume snapshot class. We'll go ahead and apply this to our cluster. Also, move it to the SPDK-CSI namespace. Went ahead and create the volume snapshot class. So after the volume snapshot class is created, for us to be able to take snapshot of our existing PVC. So we have the snapshot .yaml, yeah. So the snapshot.yaml will reference the volume snapshot class name I just created, and then the persistent volume claim which I created earlier. So before we do this, I want to be able to show data persistence, that the data that exists in the persistent volume claim can, after the snapshot, we can still be able to get that data in the next, in the snapshot, and when the snapshot is restored. So what I will do, I will go back to the already existing PVC, which I created. So first, I will go ahead and create a pod and write to this pod. Okay. So that's a simple pod with the claim name. So go ahead and apply this pod. So still creating. Okay, now great. So I will exec into the pod and write just should create directory and create a file. Okay. Sorry. Let me have this here. Just go in with bin sh. Cool. So if you look at the mount part here is the SPDK vault. So we will cd into this into the mount part in the container. So from here, we'll go ahead and create a directory. I will create a simple directory. Let's call it kcd ostra. Yeah. So we can cd into this directory, and then maybe write a simple file. Let's move it to maybe kcd ostra. Just simple test file. Okay, cool. So after we have done this, so return back to the volume snapshot. So I want to take snapshot of this part, this PVC, of this PV rather. So cat snapshot again, reference it again. So from here, so created a snapshot. So it is ready to use. So this is the name of the snapshot content which is created. So what I will do now, I will go ahead and destroy I will go ahead and destroy the test pod that is in let's say in a situation of a disaster. I'll go ahead and delete the pod. So it's going to take a while. So I just cancel. It's terminating the background. So next, I'll try to restore the created snapshot into a different new PVC. So that PVC, we called it PVC. Okay. So this is we'll create a new PVC called the SPDK-CSI PV Restore. SPDK-CSI namespace. So now we have two PVC. So so from here on the test pod snapshot, if you look closely, you will notice that the claim name is making reference to the restored PVC. So we'll go ahead and create this test pod to mount on the restored PVC that was restored from the snapshot, and then we'll check for the availability of the previous directory and file which I created to see if they exist. Okay, I'll have a new pod running. So we'll try to exec to that pod. Just copy, paste it. Okay. Okay, yeah, thank you. Right. So from the pod, we also referenced it in the SPDK vol directory. So we'll cd into SPDK vol directory, and then from there, ls, we can see the directory should exist. So we'll cd into the directory. So from here, we can cut our file that was created from. Notice we have the file that was existing from the previous the system volume claim. So because of time, I will try to rush to talk about cloning quickly. So for volume cloning, somehow similar to snapshot, but in the case you don't have to have a backup, but maybe in a situation where we want to move data, want to move our data to the next workload, maybe a particular workload needs access to that data, and you want the pod to run on a separate new workload. So what you do, you create a clone of the existing PV. So all the data that exists in the existing PV will be available in the new created PV from the clone. So if you look somehow similar to the snapshot in terms of the data source, but in this you reference the kind name. The kind name will be the persistent volume claim. And then the API group. The API group can be left empty because PVCs is part of Kubernetes API core. So by the kind name Kubernetes, we're able to find it. So also the capacity of time. Go ahead and just demonstrate this also faster. So we still have the PV. I intentionally left the PV to still exist so I can be able to show the clone. So we still have the PV from the first PV that was created. So we'll try to have a clone of that PV. So cat PVC clone here. So go ahead and apply. Okay. So we'll just run the clone. We have a total of 3 persistent volume. No? Persistent volume claim. So what's next? What I will do next is to mount a pod to this clone PVC. Look, the claim name referencing the PVC clone. So what I'll do, apply. Apply. Okay, still creating. Okay, it's created. Okay, so just copy and clone, paste it. Okay, also read reference to the mount path SPDK vault. So we seed into that mount path. Then we ls. So we also have the data KCD Ostra. So we can cut. So the data also exists in the clone. So based on the routes or your use cases, you can decide to either clone your persistent volume or do a snapshot for backup of your persistent volume claims. Thank you. So the last part. So this is just the demo I just showed. So maybe any question for me? Sure.
Right. First, a big round of applause, please. Great insights into the world of storage. Just due to time, Israel won't be leaving, so if you have any questions, just please catch up with him during lunch. I see you back here at 1:30 for the next session here in Hall 6.
So I would like to also maybe can meet him outside to discuss more on volume expansion and volume resize, and one of the certain things we're building in Simply Block CSI. So a lot of things building in Simply Block storage, a lot of things going on there on SPDKs and also fast storage and high performance storage with low latency and high throughput. We can discuss more about that. All right, thank you.